Let's see some linear transformations in action with R. We're only going to add a couple things to our little toolbox here for R programming, and this is it. We are going to be able to create a plot and add points. This is something we saw before in episode 3. The only thing I'm adding here is the ability to change the color of the points, which is, sort of a little cosmetic nicety, but also is going to allow us to see the difference between the original points and the transformed points when we do a linear transformation, as we'll see. And then I'm going to add another command here called arrows, which is a way of drawing an arrow from one point to another so we can see the path that the transformed value took. So notice that you give it a from x and y value, so that's the x and y value of the point that you want the arrow to start from, and then a to x and y value that shows where you want it to go to. And then you can also color the arrow like this. By the way, all these commands have tons more options if you want to look them up. This is just the basics to sort of illustrate what we want to do here. So here's what I'm going to do in this very brief segment. We're going to make a function, and the function is going to be called plot transformation. And what you're going to do is give this function a matrix when you run it. It's going to be a 2x2 matrix because that's all we can really plot is two-dimensional things. And what this function is going to do is generate a bunch of random points and plot them on the xy axis, and then multiply the matrix times each one of those points to get the linear transformed version of those points, and then plot the new transformed points. And we will plot them in different colors and show an arrow between so you can see the effect that a particular linear operator has. Okay, so let's get started. If I go into RStudio here, we're going to make a function called plot transformation. And remember the syntax, we're going to say that is a function, and we'll label our argument A. Again, this could be anything we want. This is just going to be the name that we, the function, call the matrix that we are given. And here's what we're going to do. First, let's set up our plot by doing this standard thing. And we'll set our x and y limits to go from -5 to 5, just so it's kind of symmetric there. Another thing, by the way, which I may have done, if not, it's a nice little thing. AB line is a function that does a lot of things, but all I'm going to do here is say h equals 0, v equals 0, and what that's going to do is plot axes for us. Okay, so if I save this thing and then I run it over here by saying, oh, let's make a matrix, we'll call it M, and let's set that to be a matrix. Let's use the identity matrix first. 1, 0, 0, 1. And we'll say by row equals true, although it doesn't really matter in this case, and n row equals 2. So M is that matrix right there, and I'm going to call plot transformation and give it M. And that makes a plot over here and just puts our axes on here, right? So that's all I did with this AB line thing. Now, the meat of the function is going to be this. I'm going to make a little loop. And remember, this is a way of making a loop go through 100 times, we'll say. We'll make 100 points. And each time we want to get a random x value. Let's use our runIf function. And the result from that is going to be between 0 and 1, a random number between 0 and 1. If we multiply that by 10, it's a random number between 0 and 10. And then if we subtract 5 from it, then it's going to be a random number between -5 and 5, right? So basically that's going to make a random x value somewhere where our axes can see it. And then we'll do the same thing with a y value. And then let's make a point out of that. And the way we make a point is we say, let's make a vector, which has the x value we made and the y value we made, right? So that's just using the C function to create a vector. And then let's use our points function, as I mentioned on the cheat sheet. And we'll give it x val. Actually, let's give it point of 1 and point of 2, just to show we can get the things out of the point vector we made. And let's say our color is going to be blue, just because I like blue, right? Okay, so far we haven't actually used the matrix A yet, right? That's going to come up in a second. If we source this and run our plot transformation again, we're going to get a bunch of different blue points. And if we run it again, we're going to get a bunch of different blue points, right? Because every time we run it, it's going to be random. And by the way, if you don't like that shape, which I sort of don't because it's kind of open, you can say PCH, and you can give it any character you want. You could give it an S for Stephen, and then it would plot a bunch of S's. I don't like that either. What I'm going to do is this kind of weird one where I'm going to say PCH equals 19, and for whatever reason, 19 is set to be this nice little dot here, so I kind of like that dot. That's all the PCH thing does. Okay, so I plotted my points untransformed. Now I'm simply going to plot the linear transform version of it. And of course, the way we do that is we take our matrix and we do the dot product of that matrix with our point. Now, that right there is the linear algebra part of this program, right? Everything else is essentially just R stuff to set up a plot and make random points and all that kind of stuff. But the thing that matters is this thing right here. And what I'm going to do after I compute that product is I'm going to say transformed point gets that. And then I'm going to plot the transform point. So I'm going to use my points thing, and I'm going to say let's plot transformed point of 1, transformed point of 2, because that's the x and y coordinates of that. And I'm going to make it a different color. We're going to make it red here. And then I'm going to do arrows, and we're going to say go from point 1, point 2 to transformed point 1, transformed point 2, and we'll make the arrow red. Okay. Now we're going to run this, and it's probably going to look funny when we use this M, which is the identity matrix, because it's all going to plot on top of itself, right? So if we run that, we get this here. The warnings are basically because we have nothing to do an arrow. I don't know if you can tell the difference between those plots, but we actually have kind of a little bigger red circle here around it. Actually, they'd be totally hidden if I would have used the PCH equals 19. Again, that's just a cosmetic thing. Don't get distracted by that as far as the linear algebra thing. And so if I run it, all you see is red points because they're plotting right on top of the blue, right? But now let's make a more interesting matrix. So let's make a matrix N, just because that's the next letter. And let's make it be 2, 0, 0, 2. So now we've got this thing right there. And now if we do the plot transformation and we say plot it on N, we're going to get this, right? So every blue point here has been moved out, scaled to double, right? Because we're multiplying it by this matrix right there. And the effect of the 2, 0, 0, 2 matrix is simply to expand the x and y values equally in both directions. By the way, it's a little hard to see that it's equal here. Maybe I'll shrink this so that it's more of a square. And now you can see more that it's moving, equally in the x and y directions, shooting it out from the center, right? And if I were to make another matrix, let's call this one O, and set that equal to, how about 0.5002? So what's this matrix going to do? See if you can figure that out before I run it and see if your intuition is right. And this is what it's doing. So it is shrinking the point in the x direction and expanding it in the y. Shrinking it in the x direction, expanding it in the y. Shrinking it in the x direction, expanding it in the y. So that's what that transformation does. Let's run another one. Some other examples we did one where it was this flip on the y-axis thing, right? So negative 1, 0, 0, 1. If I look at that matrix, and now let's plot that transformation, it's going to look like this. So notice it's taken every dot. It's a little hard to see here because there's so many dots. I could make this less than 100 if we wanted to make it a little bit easier to read. In fact, let's do that. So let's run it with just 20 points. And if you can see this, it's taking like that blue point and it's transforming it over there. And it's taking this blue point and it's transforming it over there. And it's taking this blue point and transforming it over there. So it's simply reflecting along the y-axis, right? And you can see the effect of a lot of different things. Let's make one that goes negative 1, 0, 0, negative 1. I called it P again. I overwrote the other P. That's okay. And what that's doing is it's taking this point right here and mapping it down to this one. And it's taking this point and mapping it up to this one. So it's now reflecting it through the origin because both the y and the x-axis values are getting flipped. And if you remember the one we did, which was the 0.707 thing, right? That was a little bit weird. We said let's map it to 0.707, negative 0.707, 0.707, 0.707. So the Q matrix looks like that. And now if I plot my transformation Q, this is the rotation thing, right? So it takes every point and rotates it 45 degrees, and we get this sort of whirlpool type phenomenon. I think that looks a little cooler if we have more points. Let's go up to 80. And you can see that it's swirling around kind of like a toilet bowl when you flush it or whatever, right? And we could make it go the other way if we wanted to. And we could also set this to different things, right? So one thing we had was 0, -1, 1, 0. So if that's my Q, then if we plot the transformation Q, now if you can see it, it's going 90 degrees to the right. Each point is going a full 90 degrees instead of a 45 degrees, right? And you can set those to anything you want. So this is kind of an interesting way to see the effect of a linear transformation, right? So pretty simple episode. The big lesson to get, number one, is that there's such a thing as a linear transformation. We can view any matrix as transforming a vector in one dimension to another dimension, which might be the same dimension. If it is the same dimension, we call that a linear operator. The other thing we learned is that every matrix has a rank, which is simply the number of linearly independent columns, essentially the number of yellow dominoes that are in there. And that if it's not of full rank, if the number of linearly independent columns is less than the number of columns, then there's a null space that is bigger than just the zero vector, right? So that means there are vectors other than just the zero vector that we can take the transformation of with that matrix and get the zero vector. And in fact, the dimension of the null space, called the nullity, the dimension of the kernel, is actually, if you add that to the rank, you end up getting the dimension of the matrix. So if I have a matrix that's 50 by 50, and it only has rank 48, that means there's a null space dimension of 2, which means there are essentially 2 different degrees of freedom that I have to play with in choosing vectors that will map to the zero vector. And we will see that in action when we look at our application section in a couple episodes. Take care. Catch you next time on All the Math.